Right, the normal distribution. So this is kind of the most well-known distribution in statistics. So I'll just sort of spend 5-10 minutes just explaining what it is and what it looks like. So for example, we might have a large number of 1 kilogram bags of sugar are weighed. I seem to like this example in books and stuff, so I thought I'd show you, but we'll look at some other ones as well. So if you're weighing out a kilogram, then we can draw a graph of the frequency against the mass. And you're in a bit of a rush, you're weighing up lots of bags of sugar. Most of them you'd expect to weigh a kilogram, so that's going to have a high frequency. But it may be that some of them you put a little bit too much sugar in, some of them not quite enough, and so you'll end up with this shape which is centered on the mean, and you get this bell-shaped curve, and that is the shape of a normal distribution. And the two key things is it's symmetrical about the mean, and the second thing is it's got more values close to the mean than further away. So last year we looked at the binomial distribution, where you have success and failure, and we looked at the graph shapes of that, and we did some hypothesis testing. We're sort of mimicking that, but with the normal distribution. So this one is always symmetrical, unlike the binomial, centered at the mean, and it has more values close to the mean than further away. And if that is true, then you can model data with a normal distribution. So it may not be that it fits perfectly, so that may be your perfect normal distribution, but when you looked at all your bags of sugar, it may have been doing something like that. So you're not expecting a perfect fit, but if these two things are true, then data can be modelled with a normal distribution. So we're modelling with these distributions. This pen is finally running out. It's been going for ages. So hopefully that's clear. Sorry, smudging. Just for interest's sake, so the normal distribution was originally called the error law, and it rose from the work of 18th century mathematicians and astronomers who were calculating the orbits of stars and planets. They found that they had to take into account the effect of observational error. So you sort of have your errors coming both ways. This law described how values that the mathematicians and astronomers observed were clustered around their average, and gave the watchers estimates of the chances of an error of a given size. So that's where we're going with this. We're definitely heading towards probability. I'm pleased to know that you love probability. So another example that you could model with a normal distribution would be heights. So adult male heights. So the mean is equal to 5'10" on average, and the standard deviation is 4 inches. And so the way this would look as a normal distribution is you get this symmetrical curve. Mean is at the centre, so that's your 5'10". And then you're expecting 95% of your data to be within 2 standard deviations of the mean. We'll come back to that. So that takes you right up to 6'6", doesn't it? And then down to 5'2". So your curve is going to look something like that. The equation of that curve is y is equal to 1 over the standard deviation times the square root of 2 pi e to the minus a half x minus the mean over the standard deviation squared. You don't need to know that, it's in your formula book. But that's true for all normal distributions. And the thing to really take from this is that you've got your y and you've got your x, and the rest of it is dependent on the standard deviation and the mean. So it's those 2 parameters that give you the shape of the curve. So if we've got a continuous random variable, so height is a continuous variable, and someone's height you'd expect to occur randomly. So we did some work on discrete random variables. These are continuous. Has a normal distribution. There's no gaps in the data. Then we can model that as x has a normal distribution, and the 2 parameters are the mean and the standard deviation, but it's actually written, the parameters are written as the standard deviation squared, not just the standard deviation. So just to remind you, mu is the mean and phi is the standard deviation. It's actually the population standard deviation, that one. Population mean. So we've used that notation a lot for the mean, but that's for the mean of a sample. And mu is the mean of the whole population. So in this case, a whole population of males, not just a sample of them. Just out of interest, not to be sexist or anything, so females, the mean average female height is 5'5", and the standard deviation is 3.5 inches. So you're expecting 95% of female heights to be within 2 standard deviation of that mean of 5'5". So that's just kind of a rough view of what a normal distribution is, what things are characteristics of it. So it's a symmetrical distribution, situated symmetrical about the mean. So it's a continuous distribution is what I meant to say. It's symmetrical about the mean, and there's more values close to the mean than further away. And this equation here, which you don't need to know anything about, gives you this nice normal distribution, bell-shaped curve.